All right, so now we're going to get into carbon-14 and some other things here. We're not going to focus too much on carbon-14, but you need to know that carbon-14 is an isotope. It is mildly radioactive, and you see it starting down there in the bottom left, that as you live, we absorb a certain amount of C14. Now this depends on where you're at. Different areas of the globe, different levels of the Earth have different carbon-14 ratios during the time of the organism. We really don't know how much is there. What we do know is it has something called a half-life. So while this thing dies and becomes fossilized, a certain amount of this carbon-14 is going to decay and turn into something else. So we burn the fossil, and we find out how much carbon-14 is there, and then we can determine by the half-life, which we're not going to get into, how much carbon-14 should have been there, which tells us how long ago this thing lived. And you see the little radiation counter right there on the other side. Wonderful. This isn't great. It's okay, but remember, it all depends on how much carbon-14 was around that area when this organism lived, and how much it absorbed and how much it kept. So there's a lot that goes into carbon dating with carbon-14, but for now it's the best we have. So moving on. Nuclear versus chemical reactions. It's imperative that you understand the difference between a nuclear and a chemical reaction. Okay. Nuclear reactions form a new isotope or form a different element. Okay. Chemical reactions form a new substance based on the elements in the reaction. So from here, we're going to go from a uranium to a thorium. Okay, two different elements. Whereas another one, we would start with a sodium and a chlorine and form a new substance called sodium chloride. We can bounce that out if we wanted to. So you see the differences there. One's a new element, one is a new substance. Nuclear reactions have a large amount of energy, whereas chemical is a small amount of energy. Energy comes from the binding energy of the nucleus in nuclear reactions. Remember, it's all about that nucleus. Whereas in a chemical reaction, it's all about the bonds. Remember, that's where energy is stored or required, is the forming and breaking of those bonds. And finally, it involves a change in the nucleus. We can say change in nucleus. Whereas the chemical involves a change in valence electrons. So chemical is all about the electrons, whereas nuclear is all about the nucleus. Okay, that should make sense. We'll go ahead and state it for you. So when you're writing these nuclear reactions, you've got to, one, pay attention to know what you're starting with, get the right chemical configuration, know the symbol for the radiation, and then just do very simple addition and subtraction to find out what's going on next. You can write those down if you want. So for instance, we did this example problem. Magnesium-29 goes through beta minus decay. So what's going to be our new symbol? Well, first we're going to focus on just the top. So we'll do just the top right here. The top is 29 and something equals something. So we can change the yield sign to an equal and do 29 equals 0 plus something. So what plus 0 equals 29? Well, that would be 29. So our mass number has not changed. Now let's go look at the protons. 12 equals minus 1 plus something. So what plus negative 1 equals 12? Well, that would be 13. So now we got 13 here. Then you got to go along the periodic table and find what element number 13 is, and that will be aluminum. So aluminum 29 would be our result. And that's how you would write it. So it's really not difficult at all. So let's go through some of our emissions. So the first one is alpha emission. Remember, alpha is a helium nucleus that is going to come off of some atoms. So you see the picture here. It starts with americium, 241, ends up with neptunium, 237. And here's our alpha particle that's actually going away. It's decay. It's alpha emission, alpha decay. So let's figure out how this works. I'm going to change the yield sign to an equal sign. So 222 equals 4 plus something. Okay, so 222 minus 4 will equal 218, will be our new mass number. Then we'll do the bottoms. 86 equals 2 plus something. So 86 minus 2 is 84. can always go back and check your work. 84 plus 2 equals 86. Element number 84 is going to be polonium, PO. And write the nuclear equation for alpha particle. That's what we just did. Oh, different mind. So write it for if we did the alpha particle emission by uranium-235. So uranium BU, 235 is the mass number. Look on the periodic table. You find uranium is number 92. And we're going to emit an alpha particle. So yields, alpha particle, is 42Hg. That's why it's so important to know those symbols. Plus something. So now we're going to do the top. 234 plus, or equals, sorry, 234 equals 4 plus something. So 235 minus 4 is 231. We're going to the bottoms. 92 minus 2 is 90. And, oops, this is 96. And then 90 is element thorium, TH. Remember, you match up that bottom left number to find the element. That's all it is. So next you have beta emission. This looks like to be beta minus emission, but we can just switch this negative to positive for beta positive, but we'll specify beta positive when we want beta positive. Anytime you see beta, assume it's negative. So, see, it's just an electron being shot out. Fill in the missing particle. So 27 is something plus 0. So that's the top number is clearly 27. And then 12 minus negative 1 is going to be 11. Nope, it's going to be 13. So 12 minus negative 1, that means plus, it's going to be 13. Element 13 is aluminum. So now we're going to do the beta emission for iodine 131. So iodine, the mass number goes on top. Iodine is number 53. Draw the yield sign. We'll do beta minus. So 131. Oops, not plus. Shoot. Plus. So 131 minus 0 is 131. 53 minus negative 1 is 54. Element 54 is xenon. Xe. See, this is easy. Now, positron emission. Now we're just going to change the symbol of the beta to a positive 1 instead of a minus 1. Work it the same way. Top number would be 40. 39 minus 1, or sorry, 19 minus 1 would be 18. Element number 18 is argon. Then write the positron emission for oxygen 15. So O, 15, 8. Decays or yields into alpha particle, or not alpha particle, into a beta positive particle. And it'll be 15 on top still. And over 7, number 7 is nitrogen. There we go. Okay, now electron capture. The thing with electron capture is, this one's unique, is that here we're combining an alpha particle to what we started with. So you see at the very bottom, or sorry, we're combining a beta minus particle to what we started with. So you see now it's in a reactant. So it works the same way. 125 plus 0 is 125. And 53 plus negative 1 is 52. Element 52 is tellurium. There we go. So now do the electron capture for sodium 22. So Na, 22. Number is 11. Since we're capturing the electron, we're going to do here. Minus 1, 0, E, there's our beta minus, yields 22 for the mass number, 10 for the atomic number. The element number 10 will be neon. So that's the only thing, you're capturing it, so it needs to be written in the reactants. And finally, gamma emission, nothing happens. Okay? It's just energy. So you can see we started at polonium 240, we're end up at plutonium 240. Nothing changes. So the way you would write this, you do PU, 240, 94, decays into a gamma particle, which would be Y with a 0 and a 0, and the exact same element. Sorry, this is sloppy. Should give myself more space. That's all there is.